Okay, so now finally we go into the last topic, principal value. We want to evaluate minus infinity to infinity f of x dx. Okay, all right. Um, good definition. Uh, the principal value of this integral is the following: PV. We define it as the following: limit as r goes to plus infinity of minus rr f of x dx. Okay, so let me motivate this definition. An example. Um, so consider the integral of for f of x equal to x, right? So this is the graph, and this is the area we're looking for. Now clearly this seems to be infinite, right? So this is infinite, and this is also infinite. But this is negative infinite, and this is positive infinite. So the principal value of this integral is what? Minus r yep. So this is x squared over 2 minus r2r, right? So let's see, what is it? R squared 2 minus r squared 2, right? Because, okay, let me write it like this. So these two cancel out because the minus becomes plus when you square it. So it's 0. That's the principal value, right? And that's what you want. You want to say that these two areas cancel each other out. So here's a bad definition. A bad definition is limit as r goes to infinity. Let's say I take, I don't know, minus 2r and r, right? Like asymmetric. Well, in that case, what do I have? Um, I have r squared as before, but then I get, 4r squared over 2. So I get minus 2, minus 3 halves. No, sorry, minus a half. No, no, 3 halves. Yeah. So I get this guy, which is minus infinity. And that's not defined. So this principal value is uh, well posed, especially for symmetric functions. Okay, anyhow, so that's what is called principal value. There's many principal values. This is one of them. Um, Cauchy principal value. There's many types. Hilbert. Okay. Um, okay, that's good. Okay, now to use residue theorem, to evaluate star, we have to move into complex. Okay, let's see. Good. So here's the trick. Consider the following contour at 0 minus r, r. And this is a semicircle. So now we're in the complex, right? Um, okay, so let me write it as gamma r if you like. Some people write CR, doesn't matter. Okay, so we have a contour C and we split it. We have a minus r to r, and then we have this semicircle. Okay, all right. Okay, so what? Well, look what we have. This guy is the PV. So if you take r to infinity, this guy is equal to the principal value of your integral. Um, so the answer is inside here, meaning, let me specify. Um, this guy, it will equal to something by residue theorem, right? So you'll have some answer. I don't know, call it um, A naught. This is what you want, and hopefully this will go to 0, and we will explain how. So putting these two together, you get that A naught is equal to this. So yeah, it's equal to the principal value of your integral. And that's the whole technique. Okay? That's the whole idea. Let's do an example to give you a flavor. Okay. So evaluate the real integral, the principal value x squared minus 2x plus 2. Okay, that's good. So yeah, this one was what? It was the limit of this guy. Okay. Good. All right. So let's look at the complex version of it. All right. So what do I mean by that? Well, uh, what we do is wherever we see x, we put z. Okay. So z squared minus 2z plus 2 dz contour c, and this is the contour. Let me write cr. Okay. So that's the contour, and we split it. So minus RR plus the semicircle part. Okay, fine. Claim. The second term goes to 0. Yeah, let me do that first and then we'll do residue. So let me first make this term disappear. Right, okay. So let me take, so yeah, you can in fact expand this, so let me do it here. So this is z minus a, z minus b, where a is 1 minus I, b is 1 plus I. Okay. All right. Now this is a circle, okay? And it's a circle of radius r. So let's do polar coordinates, 0 to pi. We put pi because this is a semicircle, has angle pi. And we have r ei theta minus a, r ei theta minus b, and I r ei theta d theta. Okay, that's polar coordinates. And then let's do triangle. So okay, and ei theta has norm 1, so you just have r. Okay, good. Now what? Almost there. I have to take a limit in r. Um, right. Now do reverse triangle. Let me write it here. What is a reverse triangle? So reverse triangle is when you have a minus b is bigger than, sorry, um, x minus y is less than the norm of x minus the norm of y. That's reverse triangle. Okay, good. But now this is reciprocal, so it's upper bound. Is that okay? Now you might ask, why do this? I want to do it because I want to get rid of this ei theta. So what happens here is this guy becomes 1. So you have r minus a. And well, r is positive, so that's fine. And minus b. You see there is no ei theta. Theta is gone. So this is constant in theta. So you have pi, right? R over r minus a and r minus b. Okay. Now, what was our claim? Our claim is that this integral is 0. Okay. And indeed, this behaves like r over r squared, 1 over r, which goes to 0. So indeed, um, the CR integral of f goes to 0. Okay, good. So that's the first step. Second step, let's just evaluate residue theorem for our guy. So z minus a, z minus b. Let me write them down because now we need them. So 1 minus I, 1 plus I. Okay, now I have to do residue. All right. Let's see. So which ones are inside the contour? So you have two poles. you have to answer the question which ones are inside. So let me draw them. 1 plus I, it's over here. 1 and 1. What about this? 1 minus I, it's down here. Okay, so only um, only 1 plus I is inside the contour. Okay, so you only have one residue. So that integral is equal to 2 pi I of residue of what is it, f at 1 plus I. So 2 pi I z minus a z minus b times, let me write it here, z minus a evaluated at z equal to a. And so you get a minus b, which is just 1 plus I minus 1 minus I. So you get pi. Okay, so now here you can finish. If you're in the final exam, you don't have to tell us anymore. But let me tell you what has happened. Okay, so we have our function, we have our limits. So here you can finish. But let me explain you what happened. Okay, so you have these two guys. We just showed by residue theorem that this is equal to pi. Okay, but it doesn't depend on r. As you can see, there is no capital R. So now take limits in R on both sides. Okay, so you have pi is equal to the limit of R of this guy plus of this guy. And we just showed above that this guy is 0 once you take a limit. And this guy, we define it to be the principal value. And that's it. We found that the principal value of our function is pi. Okay, so let me write down what the function was. Dx. Okay, so that's that. Okay, so let me give you something to make your life easy for showing this limit. If you like lemma, you can use this. Suppose you have gamma r pz over qz dz, where p is a polynomial of degree n and q of degree m, but bigger than n plus 2. Okay, then gamma r pz over qz goes to 0 as 1 over r. Okay, all right. And let me do a quick proof. So as in the example, we do polar. So if you do polar coordinates, PI theorem, QAI theta with R. Okay, do your triangle and expand. So you have Rn with lower powers and Rm with lower powers, R d theta. Okay, so then again, I won't go into the details, but if you do reverse triangle, you get um, your Rn plus 1 lower order terms, and then Rm lower order terms. But in the limit, all it matters is the highest order. So let me say that here. By L'Hopital, you can just look at the highest order. So you have m minus n plus 1, but m is bigger or equal than n plus 2. So this is, is r less than r, which goes to 0. Okay, all right. Um, okay, let me do one more example and that's it. Just to showcase this lemma. Evaluate PV x squared plus 1 squared. Okay, so this is a ratio of polynomials. First complexify. So we have c and then z squared plus 1. Okay, good. Right, we split as usual the function and the semicircle. Okay, so now let's look at this guy. Let's just apply the lemma. P is z squared, Q is z squared plus 1 squared, has degree 2, and this guy has degree 4, which is bigger or equal than 2 plus 2, n plus 2. Okay, so the lemma applies. The lemma applies to give, to give that z squared plus 1 squared dz goes to 0 as r goes to plus infinity. Okay, so this guy is out. We can ignore it. Now what you have is you have principal value of your integral f of x. Okay, and now we have to do residue, and that's it. So we have this contour c, z squared plus 1 squared dz. Okay, so let's do residue. So 2 pi I residue of what? So we have to find the poles. Let's factor this. So we have z minus I squared. Let me write inside. So the poles are minus I and plus I. Okay, and here's the contour, and here's the pole, the two poles. But the only pole that matters is the one inside. So we only have a single pole at z equal I. So f of z at I, and that's it. There is no other pole. And as you can see, it's order 2. Okay? Alright, because I want to keep going with this, let me just write down what you have to evaluate, and I will evaluate for you. So z squared, so z minus I squared, z squared. So you take one derivative because it's order 2, and you evaluate at I, and long story short, you get pi over 2. Okay? So the principal value of our integral, so the limit of this is pi over 2. Okay, thank you. Actually, let me write it here. So minus infinity, infinity is equal to pi over 2, which is incredible. Okay, thank you.